To design algorithms, we need an abstract model of a parallel computation and a way to write down the algorithm. This lesson is about one such model, which is sometimes called the dynamic multi-threading model. It has two parts. The first part is that a computation can be represented by a directed acyclic graph, or a DAG, sort of like this one. Each node is some piece of computational work or task. Each edge is a dependency, which says that a given task can't start until all of its predecessors have completed. Now, from the point of view of exploiting parallelism, a good DAG is one that has relatively few dependencies compared to the number of tasks. After you learn how to analyze abstract DAGs more precisely, we'll arrive at the second part of the model. It's a pseudocode notation, or a programming model, for writing down the algorithm. This notation will be defined so that when you execute one of these algorithms, it generates a computational DAG, at least conceptually. Now, one caveat before we start. You may have done multi-threaded programming already using libraries like pthreads or Java threads, where your program explicitly creates virtual threads and then assigns units of work to them. If that's the case, you need to forget what you learned, at least for this lesson. The pseudocode notation that we'll talk about separates how to produce work from how to schedule and execute it. That means that you focus on creating an algorithm that has a nice DAG. Separately from that, there will be a physical multi-core machine and a runtime system that, given your DAG, figures out how to map it to cores and execute it. Now, there will be some limits to the kind of DAG you can produce in the model we'll describe, but I hope you'll see that it's still a really natural, elegant, and powerful way to express a parallel algorithm for a broad class of interesting problems.